Hello, everyone. Welcome to the solved paper of the Fastpapers UK Cambridge IGSCE paper 4. So hopefully everyone had a good exam and they're feeling prepped and they're feeling good for the examination up ahead. If you've come this far, then you have nothing to worry about. You've probably studied as much as you can. So you just have to be confident in yourself. And we know that you're going to do well. Just don't freak out, just relax, and yeah, just believe in yourself, and we're going to go through this paper real quick. Hopefully it wasn't too difficult. So we're going to start with the first question. Typically, we see that these types of questions are pretty common. So first question, nothing too difficult. Using numbers only. So this is important over here. They're saying that using only numbers. So here you don't have to write in whole sentences, right? You can just write down the exact number that they want. So over here, they're talking about percentage of nitrogen in clean, dry air. About as straight cut a question as you can get in one of these question papers. So the answer for this, obviously, is going to be 78. So now you can add percentage. You don't have to, because again, the thing they say is that using numbers only. So you don't have to add percent, but you could if you want. So you won't lose marks if you put it, and you won't lose marks if you do put it. Next, another very straightforward question. What is the typical operating temperature of the contact process in degrees Celsius? So again, the conditions are pretty much known for you all. So this is going to be 450 degrees Celsius. So you don't have to put degrees Celsius. They've already told you that it's in degrees Celsius. But again, if you put it, you don't lose marks. And if you do put it, you're fine. If you don't, completely fine as well. Next question, what are the number of metals in period 3 of the periodic table? So if we take a look over here. So period 3 is going to be, if this is your first period, oh, sorry, forgot over here. Sorry. So this is period 1, this is period 2, and this is period 3. We've got sodium, we've got magnesium, you got aluminum, and I think you guys have to remember that there is a stair. The stair sort of goes like this. So everything below the stairs is a metal, everything above the stairs is a non-metal. So if you take a look at the stairs over here, aluminum falls under the stairs, but silicon just sits right above it. So silicon is a non-metal in this case. So it's not, so it exhibits both metallic and non-metallic properties. So because of that, it's not a true metal. And so the number for this question will be number 3. All right, number of halogens, which are gases at room temperature and pressure. So RTP obviously means room temperature and pressure. So again, we're going to go back to our trusty periodic table. So halogens obviously are the group 7 elements. So if we take a look at them, we've got fluorine, bromine, iodine, astatine, and the last one, tennessine. So of all the halogens, the first two over here, these are obviously gases. And then bromine, so a lot of people might take a look at bromine vapor and think, oh, that's actually a gas. But that's actually just bromine liquid. And once it's in room temperature, it's sort of, excuse me, right, sorry about that. So as I was saying, so bromine is a liquid, but it's very volatile. So what volatile means is that it's quick to evaporate in room temperature, which is why even though when you have bromine, liquid bromine at room temperature and pressure, you'll notice that you see bromine vapor. So that might confuse some of you, but bromine is indeed a liquid. And so the answer to this question will be 2. Next, we're taking a look at the typical temperature for the fermentation of aqueous glucose in degrees Celsius. So the mark scheme over here has given a range, and they say that it's 25 to 35 degrees Celsius inclusive. So what that means is if you wrote 25 degrees Celsius, or if you wrote 35 degrees Celsius, or anything in between these values, then you're fine. You're going to get the mark for that. So some of you might be wondering, why isn't it 37 degrees Celsius? So typically when you think of fermentation of aqueous glucose, especially in the lab, so while 37 degrees Celsius is the optimum temperature for the fermentation of glucose, it's sort of a temperature that's difficult to maintain properly, because let's say if you go above 37 degrees Celsius, so if you look at the For those of you that have biology, you know that enzymes are a protein, so they denature at a certain temperature. So while 37 degrees is the optimum temperature for the fermentation, the minute you go above 37, you see a sharp decline in their production because they're denaturing. So it's sort of difficult to constantly maintain 37, especially in a lab environment, especially if you're a student and you're trying to recreate this temperature. So for safety reasons and to make sure that you're not denaturing the enzymes, we tend to keep it within below the optimum temperature. Like this is still a good rate. You're going to get glucose. You're going to be able to ferment your glucose at a proper rate. But if you try and get to 37 degrees, you run the risk of denaturing your enzymes and failing the process entirely, which is why they say that to keep it within 25 to 35. So hopefully that was clear. So next we're going to take a look at F, number of unbranched structural isomers of C4H8, which decolorize aqueous bromine. So when we think of something decolorizing aqueous bromine, we want to look at isomers that have a carbon-carbon double bond. And the other important thing, so we've got decolorizes aqueous bromine. That's one of them. The other thing that we need to watch out for is that it says structural isomers. So, sorry, unbranched, my bad, not structural isomers. We're taking a look at unbranched. So when we're talking about unbranched, it means it's going to be all in one. So if this, all your carbon chains are going to be within one line. So they want something like this, carbon, 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 like that. So this is unbranched. It's going sort of straight. The minute you go something like carbon, 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 and then you've got the carbon over here, then a carbon over here, this becomes unbranched. So that's not what they're looking for. The question here is saying they're looking for unbranched structural isomers of C4H8, which decolorize aqueous bromine. So your two categories for this is it needs to have the carbon-carbon double bond and needs to be within a straight line. So if we look at the compounds we've got over for this, I'm just going to erase some stuff over here just so we can working there. Let me erase the enzyme chart. I feel like I've right. Yeah, good enough. So the two compounds that they were hoping candidates would think of when they're doing this is but1-ene and but2-ene. So obviously, if we were to draw it, so but1-ene. Now remember, the one signifies which number carbon the double bond is present in. So but1-ene would look something like this. It's got the other carbons here. So this would have an H over here, an H over here. This already has 1, 2, 3, so this would have here. So that's an H, 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 H. A lot of you might be wondering, what if I draw it the other way? And that's fine. So this could also be, so this is CH3. I'm not going to draw the hydrogens, but you can imagine they're there. And then sort of like this. So these are essentially the same because if you number them, this is the first carbon from that direction. So you're counting from where the double bond is. So if you count it from this direction, this will be the first carbon with which the double bond is. And if you count it from this direction, then this will be the double bond there. So these two are but1-ene. Now the other one that we're looking at is but2-ene. So again, if I just erase, say, everything over here. Now but2-ene is interesting because it doesn't matter which way you come from. The bond is always going to be with the second carbon. So yeah, if we were to draw but2-ene over here in the space that we've created, it would look sort of like, so you've got your CH3 over here. This is your second carbon. It's got a double bond with this carbon. They've both got one hydrogen here, and this is bonded to another CH3 over here. So this is still a straight line. And it doesn't matter if you're drawing it from this direction or that direction. It's still the second carbon that has the bond with that. So but2-ene is your other structural isomer of C4H8 that decolorizes aqueous bromine. So if we take a look at all the structural isomers, so I've sort of gotten this image from the internet. So you can take a look over here. But1-ene is one of them. This is straight chain. Can't really draw on this one, but that's fine. If you take a look at the other ones, so this is 2-methyl propene. So the reason that this doesn't qualify as a unbranched is because it is branched if you take a look at it. So you can either look at it from, so if I'm drawing it, let me go to the paper over here, and let me just go up a bit. So let's draw it over here. So 2-methyl propene, CH3, all right, over here. So you've got a carbon over here, and it's got a CH3 over here. 1, 2, 3, and it's got one over here. 1, 2, 3. And then it's got a double bond with this carbon, and then this one's bonded with 2H. So the way this goes is it sort of goes either like this, or it goes like this. So this isn't branched, this is unbranched. And if you take a look at the structural, if you look at the stick formula over here, you can also see that this is branched, definitely. So that's one of the reasons why. Cyclobutane is another one. Obviously, you can tell that this is definitely branched because it doesn't form a straight linear pattern. It's kind of interesting. It sort of forms a whole square. And you've got methyl cyclopropane. So anytime you've got cyclic compounds, you're looking at compounds that sort of are branched in nature. So we've taken a look at the 6 different isomers that C4H8 can have. And by drawing out all the structures and by looking at them, we found that there's only 2 of them, which is butanene and butuene. And the others are sort of, what do you call it, more difficult to, they're all branched, which is why they don't count. All right, our next question is number of covalent bonds in one molecule of ethanol. So again, a lot of the times, whenever we get one of these questions, it's very helpful if we just draw out the compound in question. So if we're talking about ethanol, ethanol is C2H5OH, obviously. If I was to draw it out, I'm really sorry about how long this is taking. All right. Yeah. So if we draw it out, C2H5OH. So we're going to start with a carbon and a carbon. And we've got this carbon bonded to 1, 2, 3 hydrogen. So 1, 2, 3, and then it's like this. And it's bonded to another here, 1, 2. And then this O, oxygen, is bonded to another hydrogen. So if we count the number of bonds it has, we got 1, we got 2, we got 3, we got 4, we got 5, can't forget the carbon-carbon bond over there, 6, 7, and of course 8, which means that our answer is inevitably 8. So again, it helps to draw out these structures, and whenever you do, you'll find that the answer sort of comes to you much more easy. All right, the last question. The number of carbon atoms in one molecule of propyl butanoate. Now, whenever you get these kinds of questions, it's helpful for esters because they're already telling you from the name how many carbons you can expect. Because you've got propyl on one end and you've got butanoate on the other. Now, let's say, for example, in the exam hall, you have a brain freeze and you're not exactly sure, oh my God, is it alcohol and then acid? Is it acid and then alcohol? Oh my God, how am I going to calculate this? It's fine. You read the question and it says number of carbon atoms. So you don't need to remember the formula. You need to remember what comes first or what comes second. You just simply relax and you realize that propyl always results in 3. So propanol, it has 3 carbons. Then propane. So those are all 3 carbons. And butanoate, it comes from butane or butene or the ones that we did earlier, and that always has 4 carbons. So if you add those 2 together, then you know that you're going to have 3 plus 4, which is 7 carbons. And if you remember that, then you'll be fine for all of that. So the answer is 7. So that was a very, not too complicated 8 marks over there. Hopefully you all got that right. And if you didn't, hopefully you're able to understand where you went wrong in some cases, or maybe I could give you some tips on what to do next, on what you can do if you encounter these types of questions. So let's move on to question number 2. All right, so question number 2 starts off very simple. Identify the element in group 2 which has only 5 occupied electron shells. So again, let's take a look at our periodic table over here. going to clear up the clutter a bit because we're done with all of this. So they say we have to identify the element in group 2. So this is group 2. And now, obviously, we take a look at beryllium. So it has 4 electrons. So if we do the dot cross diagram, it's going to have 1 over here, 1, 2, and then 1, and then 2. So that's not what we're looking for, right? We're looking for 5 occupied electron shells. So in the same vein, magnesium has 12 minus 4, 8 more electrons. So if we do 8 more, that means that this entire shell will be filled, and then you're going to get another extra shell. So we're still not at 5. We're still at max 1, 2, 3. We're at 3. Let's take a look at calcium. Calcium again has 8 more than magnesium. So if you take a look, 1, 2, 3. So calcium is going to have a 4th ring, but we're still not at 5. So it's not beryllium, it's not magnesium, it's not calcium. So if we look at strontium, so it's now you notice that there's a huge jump between this and this. So strontium has 38 electrons, which if you were to do the dot cross diagram, then you would find that it does indeed have 5 occupied electron shells. So we're going to write down the answer over here. You can write it either in full form or you can write the element. So I'm going to go SR. All right. Second question. This is a very popular question. I feel like if you've been doing practice papers, then you have encountered this question a lot of times. Name and describe the type of bonding found in elements in group 2. So group 2 is obviously metals. So metals, they all have the same bonding. It's metallic. Now, whenever you get a question about metallic bonding, here are some of the points that you need to remember. So this is a 4-mark question. So you're going to get 1 mark just for writing metallic bonding. So your other 3 marks come from the following 3 phrases that they're looking for in your answer. Number 1, you have to mention cations, which are the positive ions. So back in school, I would remember this by thinking that cats are positive. So like positive. So this is just in case you guys have trouble remembering, but because of this, I never forgot cations were positive or negative. Anyways, so you have to mention cations have an attraction. So you have to mention that they're positive as well. Now this is the important part. So it's not enough to just write electrons. It's not enough to write negative ions. You have to write the delocalized sea of electrons that have a negative charge. Have a negative charge. So that's what you need to write. So your first mark is going to be for writing cations and that they're positive ions. Then you have to say that they have an attraction with the delocalized sea of electrons that have a negative charge. So that is the result of, that's what happens in metallic bonding. This is another fun question that a lot of IGSCE questions say. Give 3 observations. So when a piece of calcium is added to some cold water containing universal indicators. So this is important. So you have a universal indicator in place. A reaction takes place. Give 3 observations. So this word is very important. Whenever you see observations, they're not looking for specifics, okay? So you don't have to mention that, let's say, hydrogen is being produced or that calcium hydroxide is being produced. Because at the end of the day, you're not actually seeing, by observing, you can't tell what's being produced, right? So while we do know that chemically, observation is what we can see, what we can smell, what we can hear. So because of that, when you're adding calcium to water, the first thing you're going to see is effervescence. So what is effervescence? It's basically once you add the effervescence. So you're seeing there's fizzing happening, and not fizzing, you're seeing sort of like whiffs of gas come out, from the calcium. So you're observing that. What you're also observing is that the calcium starts to get smaller because the solid is dissolving. So you also have to mention that. solid is dissolving. And here's the thing. So usually these type of questions are worth 2 marks. So this is your 2 marks already. But because it's a 3-mark question, they had to introduce another variable that you need to identify, which is the universal indicator. So when you're adding calcium to water, you're producing calcium hydroxide, which is an alkaline solution. So because you have an alkaline solution, your universal indicator is going to indicate that it's an alkaline solution. But you cannot write that an alkaline solution is produced. So instead, what you're going to write is the solution now turns. So what color do we associate with alkali solutions? It's blue. So this is weird. I'm writing in red, so I'll just highlight that. Blue. So it turns blue. So that's your 3rd mark there. Name 2 products of this reaction. So again, fairly straightforward. If we write down the equation, it's going to be calcium plus 2H2O. Remember to always balance your equations. So this gives you calcium. So remember, calcium has an ionic charge of +2. Hydroxide has an ionic charge of -1. So you need 2 hydroxides to balance calcium plus hydrogen. So what are the 2 products? You're going to write calcium hydroxide, calcium hydroxide, and hydrogen. All right, so moving on to our next question. Calcium burns in oxygen. State the color of the flame. So there's a useful guide that we have. So this is the flame test. And it shows that for each ion, what type of color that you're going to get. So lithium burns crimson red. Sodium burns yellow. Potassium burns lilac. Barium burns green. Copper burns blue-green. And calcium, obviously, burns a nice, bright, I think I've got the orange red. So I'm going to do that. Orange red. So again, this is sort of those things that you need to remember. It's not so much as something that you can understand. Well, there is science to it, but I feel like you guys are, once you get older, you'll be able to really appreciate the science of that. Maybe if you do an offline class, we could look into that. I think that'd be a fun thing to explore. All right, so calcium burns on oxygen, so we've already stated the color of the flame. Write the symbol equation for this reaction. So if we just write down the equation, it's calcium plus oxygen gives us calcium oxide, because this has a charge of +2, this has a charge of -2, so you only need 1 of each. But here's the thing, you're not going to have just O, right? So this is going to be O2, but suddenly it's imbalanced. You have 2 oxygen here, 1 oxygen here. So you're going to put a 2 over here. And again, you've got 2 calcium here, 1 calcium here. Very easy fix. You just put a nice simple 2 over there, and you've got yourself a balanced equation. Crystals of hydrated calcium nitrate contain water molecules. The formula of hydrated calcium nitrate is calcium nitrate 2.xH2O. X is a whole number. State the term given to water molecules present in hydrated crystals. So I'm going to use a different color for this. So because we're talking about water, it's going to be the water of crystallization. And there we go. That's 1 easy mark there. All right. So whenever IGCSE or CIE give these types of questions where you're asked to find out the molar mass or like find moles, they usually do it step by step. And this is so that you're less likely to make a mistake. Or let's say you do make a mistake, it's easier to recover from it because you're not penalized for like messing up somewhere in between. So you're going to get 1 mark for this step. You're going to get 1 mark for this step. And you're going to get 1 mark for this step. So as long as you follow the instructions and you don't panic, it's a very easy mark to get. So let's take a look. When hydrated calcium nitrate is heated gently, the following reaction occurs. Calcium nitrate XH2O gives you calcium nitrate plus H2O. A sample of hydrated calcium nitrate is heated gently. 3.28 grams, so this is important, of calcium nitrate forms, and the mass of the crystals decreases by 1.44 grams. So immediately upon reading the question, if the mass of this crystal over here decreases by minus 1.44 grams, so what is escaping from the crystals? So you already have calcium nitrate, so we can only assume that this 1.44 gram is H2O. So this is immediately my thoughts when I read the question. So you guys might have a different thought process. You might handle the question immediately, but I'm just showing you guys what my thought process was during all of this. So the first step they're asking us to do, determine the value of X in calcium nitrate using the following steps. Calculate the number of moles of calcium nitrate that remain. So moles is equal to, this is sort of a age-old formula, mass by mR. So the mass that we have is 3.28 grams. So we're going to put that in over here, 3.28, and we're going to divide it by the mass mR of calcium nitrate is 164. Here's a good thing about CIA or IGCSE examinations. You're rarely going to get a very ugly number. So if you put this into the calculator, you're going to get 0.02 moles. And boom, so you put that in, 0.02. And if you go down, calculate the number of moles of water given off. So again, we've already figured out that if 1.44 grams, so if the mass of crystals decreases by 1.44 grams, then that 1.44 grams has to be water, because calcium nitrate still remains because the chemical equation. So same step as before. Moles is equal to mass by mR. Because it's water, I'm going to use blue. So this is going to be 1.44 divided by, I'm very sorry for my handwriting, it's going to be 18. And that's going to give you 0.08 moles. So that's your second step. That's your second mark that you've gotten. So let's say, for example, God forbid, worst case scenario, you're doing this question last, and you don't have time to get to the final step. As long as you've done these two, you're at least getting 2 marks, which is always better than getting no marks. Determine the value of X. So here's the thing. We're looking at this molar equation, right? It's calcium nitrate into XH2O. So for every 1 mole of calcium nitrate that you have, you get X moles of H2O. So if with 0.02 moles, you get 0.08 moles of water, so 1 mole of calcium nitrate is going to give you 0.08 divided by 0.02, so this is the unitary method, times 1, and if you do the math, you're going to get 4. And that's your answer. The answer is going to be 4, and that's an easy 17 marks that you've gotten for question number 2. All right, so let's move on to question number 3. A student prepares a sample of the insoluble salt barium sulfate. So this is important to note. It says insoluble. The student adds aqueous sodium sulfate to aqueous barium chloride. The student carries out the following steps. Dissolve 0.1 moles of solid barium chloride, so it's 0.1 moles of solid barium chloride in 100 centimeter cube of distilled water in a beaker to form barium chloride aqueous. An aqueous solution which contains 0.1 moles of Na2SO4 to the beaker containing barium chloride from step 1. An aqueous solution, so you're mixing sodium sulfate with barium chloride. Stir the mixture and then filter it. Dry the solid left in the filter paper. So we're drying the solid at the filter. Complete the symbol equation for the reaction, including state symbols. All right. So we're reacting barium chloride with sodium sulfate. So the question already tells us that barium sulfate is insoluble. So if something is insoluble, it's not going to be aqueous. It's not going to be a liquid, obviously. So this is just going to be a nice, very simple solid. Next, so let's take a look at what we've eliminated so far. So on this side, we had one barium. So let's cancel that out. We've got one barium here. We've got one sulfate here, and we've got one sulfate here. So all we've got left is two sodium and two chlorine. So we know of a compound that has sodium and chloride. It's table salt. It's simply 2NaCl. And for those who've had caught like a cold in this really nasty weather, I'm pretty sure all of you have been recommended to gargle salt water. So if you've gargled salt water, then you know that sodium chloride, which is table salt, is soluble in water. So this is going to be aqueous. I'm going to highlight that in blue so everyone knows it is aqueous. A why A looks like a Q. Let's make that better. A Q. All right. Calculate the mass of solid barium chloride dissolved in step 1. So if we're going to calculate the mass, so we have the moles. So we have moles is equal to mass by mR. So we have the moles. Moles is 0.1. We're tasked to find out the mass, and we can figure out the MR from the periodic table. So barium has a mass number of 137. So I can put this 137. Chlorine has a mass number of 35.5. But because we're doing Cl2, it's BaCl2, so this will be multiplied by 2, and this will have a 2. That will give us 71. So the mass is going to be moles into MR, which will give us 0.1 into 208, which is a nice clean 20.8 grams. All right, let's move forward. The concentration of sodium sulfate in step 2 is 1.25 mole per dm cube. Calculate the volume in cm cube of 1.25 mole per dm cube of sodium sulfate added in step 2, which contains 0.1 moles of sodium sulfate. So again, we're going to use the molar formula, which is moles is equal to concentration times, now since it's in cm cube, we're going to put volume in cm cube, and this is going to be divided by 1000. So let's plug in our values and see what we have. We have 0.1 is equal to, we have the concentration 1.25 times, we don't know the volume, divide by 1000. So our volume is going to be 0.1 into 1000 divided by 1.25. So if you plug that into a calculator, you're going to get the very nice clean number 80. State the color of the solid formed in step 2. So the solid that's formed in step 2 is barium sulfate. You could also argue that, oh, there's also sodium chloride. It doesn't matter. Either way you look at it, the answer is going to be white. I would use the white color to write this down, but I don't think you guys will be able to see it. It's going to be white. All right, the mixture is filtered in step 3. State the general term given to a solid left in the filter paper after filtration. Not much to do here. You either know this one or you don't. So for those of you that don't know, make sure to write this down. This is residue. Whenever you have anything left over in a filter paper after filtration, that is called the residue. All right, next question. The actual mass of dry barium sulfate collected in step 4 is greater than the expected mass. This is because the student should do an additional step between step 3 and step 4. Suggest what the student should do in this additional step and explain why the actual mass collected is greater than the expected mass. So let's take a look. Is additional step between step 3 and step 4. So when you're doing this reaction, you're getting barium chloride and sodium sulfate. You're getting barium sulfate and sodium chloride. So what could happen between this step is you might have some additional NaCl within the barium sulfate. So let's say this is your barium sulfate. So we're going to say BaSO4 over here. So you could have like small bits of NaCl stuck to this barium sulfate. Now, that's going to be a problem because when you're weighing the actual mass, all right, yeah. So you're also getting some sodium chloride stuck onto your barium sulfate, right? So there's an easy fix for this. We know one of these salts is soluble and one of these is insoluble. So all you have to do to remove this pesky sodium chloride is rinse the mass with water. And if you do that, that will rinse off any soluble NaCl stuck to the BaSO4. So that's all you have to write. You could also add as the mass may contain solid NaCl. That's it. So this next one, this is just a definition at the end of the day. When you prepare an insoluble salt from an aqueous solution, it will always be a precipitation reaction. That's one mark. State the name of a different barium salt that can be used in place of barium chloride. So barium chloride is soluble in water. So if you want to replace barium chloride, you need an equally soluble barium salt. And so you can go with barium nitrate, BaNO3, 2. So name of a different barium salt. So you can either write barium nitrate or you can just write nitrate. So let's write barium nitrate. Nice and simple. Next, a sulfate salt that can be used in place of sodium sulfate. So here you can put in any group 1 salt that you want. Obviously, you don't want anything that's too reactive or too difficult to find. So potassium sulfate is a nice substitute. Potassium sulfate. And last but not least, barium salt that can be made by this method. So we're doing a precipitation reaction, right? So we're looking for another insoluble salt. So just draw an arrow down here. We're looking for an insoluble salt. So what barium salt can you say that is insoluble? Well, what about barium carbonate? So you can just write carbonate over here actually. Barium carbonate. And we're done with question 3. So we're going to move on to question 4. Well, before we move on to that, I forgot that I didn't even write barium carbonate. All right, let's move on to question number 4. So this question, all right, so this question is about compounds of sulfur. Sulfuric acid is manufactured in a 4-stage process. Stage 1, sulfur dioxide is produced from ores containing sulfur. All right. Stage 2, sulfur dioxide reacts with oxygen to form sulfur trioxide. Stage 3, sulfur trioxide reacts with concentrated sulfuric acid to form oleum, H2S2O7. Oleum reacts with water to form concentrated sulfuric acid. So iron pyrite is an ore containing sulfur. The ore contains a compound with the formula FeS2. Iron sulfide reacts with oxygen in the air to produce sulfur dioxide. balance this symbol equation for this reaction. So immediately we've got 4 iron here and we got 2 iron here. So what if we fix that with a nice little 2? This just feels natural, right? Like this is your first instinct. You take a look, you see 4 iron here, you see 2 here, you're gonna put a 2 here. So that leaves us with 6 oxygen over here and 2 oxygen over here. So that gives us a total of 8. And over here, we can control the amount of oxygen. So let's keep that in mind while we go to the next one. So sulfur oxide, we have 4, 2, so that's 8 sulfur. So what would happen if you just put an 8 over here? Because remember, we can control the amount of oxygen that we put over here. So then we have 8 over here, and we have 8 over. So we got 8 sulfur. So if we recalculate how much sulfur oxygen we have, on this side you have 8 twos are 16, and on this side you have 2 threes are 6. That gives you a total of 22 O molecules. So not 22 O2, 22 O. So how do we get 22 O? Well, if you divide this by 2, you get 11 O2. So this will be a nice, simple 11. Complete the dot and cross diagram in figure 4.1 to show the electronic configuration in an oxygen molecule. Show outer shell electrons only. Nice and simple, keep it easy. Cross here, then 1, 2, 4, then let's say 5, 6. Boom. Blue. 1 here, 1 here, 1 here, 1 pair here. And simple as that. Nothing too hard, nothing too complicated. So we're going to move on to the next question. State 3 typical conditions for the reaction between sulfur dioxide and oxygen in stage 2. So this is straight out of the contact process. This is describing the contact process. So as long as you have the conditions of the contact process, as long as you remember what they are, which is, let's say, the temperature, the pressure, and the catalyst, then you are good to go. Because it's as simple as just writing 450 degrees Celsius. It's as simple as writing, so you can either choose between 2 atm or, so there's an or, you can write 200 kilopascals. You don't lose marks if you write, you get marks for whatever one you write. And the last one, so this is important. So a lot of people, they get excited. They see this question and they're going to write, I know this, super simple, vanadium V oxide, and they stop over here. So you have to explain why you need vanadium V oxide. So you're going to write as a catalyst. So this is important. A lot of people miss out on that. So make sure you don't do that. Don't lose easy marks in the exam. All right? All right, moving forward. Write a symbol equation for the reaction that occurs in stage 2. So that is sulfur dioxide reacts with oxygen to form sulfur trioxide. Let's take a look at that. So it's SO2 plus O2, which gives you SO3. You think it's as simple as that, but no. It's a reversible reaction. So when you're writing it, there's 2 things you need to remember. Number 1, we're going to put SO2 plus O2, the reversible reaction sign, that, and then SO3. Remember, you have to keep it balanced. So we've got 2 oxygen here, 2 here, 4, and we've got 3 oxygen here. So that's not going to work out for us. So how do we balance it? Well, if you take a look at 2 and 3, they're. So what if we put, let's say, a 2 over here? So you got 4 oxygen and 2 oxygen, and then you put 2 over here. So you got 6 oxygen, 6 oxygen, 2 sulfur, 2 sulfur. So the next one is write a symbol equation for the reaction that happens in stage 3. So this is a bit tricky. But as long as you've got your contact process remembered, So remember that you need to dissolve your sulfur trioxide in concentrated sulfuric acid. So as long as you know that, you know sulfur trioxide's symbol, you know the formula for sulfuric acid. So you're going to put that down, arrow, and they've already given you the formula of oleum. So it's H2S2O7. Just going to double check because none of us are perfect. Yeah, H2S2O7. So let's compare. We've got 2 sulfur here, 2 sulfur here, 2 hydrogen here, 2 hydrogen here. Oxygen, 4, 3, 7, 7 over here. No need to balance. This is final. Sulfuric acid reacts with carbon. The equation for the reaction is shown. Give the oxidation number of carbon. Give the oxidation number of carbon in C. So right now it's at a resting state. It doesn't currently have an oxidation number. So this will be 0. Over here, so we know that oxygen has an oxidation number of 2 minus. So if you have 2 moles of oxygen, 2O or O2, so that will be 2 into 2 minus, which means that carbon, because this is overall a neutral thing, it's not an ion, because an ion needs to see either a plus or minus here, which you aren't, so I'm going to remove that. So because of that, you need something that will neutralize this minus 4 that's being provided by the 2 oxygen. As a result, carbon will have an oxidation number of plus 4. Simple. All right, another mole question. Dilute sulfuric acid reacts with sodium hydrogen carbonate to produce carbon dioxide gas. So that's the equation over here. 4.2 grams of sodium hydrogen carbonate is added to excess dilute sulfuric acid. Calculate the volume of CO2 measured at room temperature and pressure produced using the following steps. So again, they're giving you the steps to make it easier for you to get the mark and to make sure you don't make a mistake later on. So they've given you the MR, they've given you the mass. We know the golden rule, moles is equal to mass by MR. So this will be 4.2 divided by 84. Again, you're always going to get a nice, clean number. 5. Deduce the number of moles of carbon dioxide that is produced. So let's take a look at what we have over here. So we can do sort of a molar ratio. So if we look at sodium hydrogen carbonate, so 2 moles of it produces 2 moles of carbon dioxide. So keeping that in mind, if you look at the molar ratio, this is to this. So for every 2 moles of sodium hydrogen carbonate, you're going to get 2 moles of carbon dioxide. So 0.05 moles of sodium hydrogen carbonate was produced. You're also going to get 0.05 moles of carbon dioxide. Calculate the volume of CO2 produced in cm cube. 1 mole of any gas occupies 24,000 cm cube at room temperature and pressure. So what that means is 1 mole is equal to 24,000 cm cube. So 0.05 moles is equal to 24,000. Again, we're doing unitary method. Divided by 1 into 0.05. And if you plug that into your calculator, let me plug that into my calculator, 1,000 to 0.05, gives us the nice clean 1,200 centimeter cube. And that's it with question 4. All right, so question 5. This question is about organic compounds. Organic compound Q has the following composition by mass. 50% of it is carbon, 5.56% of it is hydrogen, and 44.4% of it is oxygen. So calculate the empirical formula of compound Q. So by now we should know, if you're going to figure out the empirical formula of any compound, you take the percentage of each, let's say, element. So percentage, and you divide it by the MR. So for carbon, that'll be 50 divided by 12. For hydrogen, that'll be 5.56 divided by 1. oxygen, it'll be 44.44 divided by 16. So I know I said that you're always going to get some pretty, very clean numbers. Maybe not the case for empirical formula. So carbon comes to around 4.167. Hydrogen stays at 5.56. And oxygen comes to around 2.7775. So once you get to this number, you always divide by the lowest number that you have. So that would be 2.7775. Another. So this is also divided by 2.7775. This is also divided by 2.7775. So if we go over here, then your carbon comes to around 1.5. Your hydrogen comes to around 2.00. And obviously your oxygen is going to come down to 1. But you can't have 1.5 carbon, so what are you going to do? You're going to multiply everything by 2, multiply by 2, multiply by 2, which gives you C3, H4, and O2. All right? So organic compound R has the empirical formula CHO and a relative molecular mass of 160. So if you want to figure out the molecular formula, you're going to take the mass of empirical formula. MR, not mass. So MR of empirical formula. So this will be 12 plus 1 plus 16, which is 29. So now you take this mass and you divide the relative molecular mass. So R MR divided by MR of, so basically this MR, that gives you 116 divided by 29. And again, you get a nice clean number 4. But what do you do with this number? You multiply all the numbers with 4. So for example, if this was C3, our previous one, C3H4O2, then this would be C12H16OH. But because it's going to be for CHO, so it's going to be CHO, which is 1 into C, 1 into H, and 1 into O. All of this will be multiplied by 4, multiplied by 4, multiplied by 4, giving us C4, H4, and O4. Carboxylic acids react with alcohols to form esters. Name the other product that's formed when a carboxylic acid reacts with an alcohol. So whenever you react a carboxylic acid with an alcohol, the byproduct is always going to be, so let me switch the color for this, it's going to be water. The type of catalyst. So you don't have to mention specifically any name. So as a result, you're only expected to write acid. So you don't need to specify which acid. As long as you just write acid, you're going to get fine. Ester S has the structural formula CH3CH2COO CH2 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 CH2. Name the carboxylic acid and the alcohol which react together to form ester S. So we know that in the beginning, you're always going to begin with the carboxylic acid. So let's count the number of carbons. We got 1, 2, and 3 before we get to the carboxyl linkage. So that means this will be propanoic acid. And if we take a look at the carbons for the alcohol, 1, 2, 3, 4. So if you're going to write just regular butanol, you guys are at a stage where just writing butanol is not going to be enough. So you need to specify that this is butan 1-ol. So I think this is a change they implemented recently. Before you could get away with just writing butanol. But whenever you're going to write butanol from now on, you're going to have to mention that it's butan 1-ol. Figure 5.1 shows part of a polymer structure. Name the type of polymerization that is used to produce this polymer. Because we're not seeing any water anywhere, we can assume that this is not condensation. As a result, this is going to be addition. Suggest why it is not possible to write the molecular formula of this polymer. So you guys know that whenever you guys are doing polymers, you always give a bracket. And in this bracket, you're sort of extending this, which means it's going on indefinitely, right? So because it's going on indefinitely, we're not exactly sure what the length is. And as a result, we can't write down how many units are in this, how many carbon units. It's indefinite. As a result, you write down it's not possible to do this because it has an indefinite length, because it keeps going on and on and on and on. So whenever you write a molecular formula, it eventually ends, right? So if we take a look at, take for example, ethanol, for example, CH3COOH, it ends over here, or it ends over here, depending on which way you're looking at. But for a polymer, it sort of keeps going, so you don't know where it begins or where it ends. It has an indefinite length. As a result, you really can't write a molecular formula for that. State the number of monomer units that are needed to make part of the polymer structure shown in figure 5.1. So if we cut this, take a look, let's say we cut it here, we cut it here. So we've got nice over here, if you take a look at this. The reason I cut it at this position is that you need to figure out how many carbons are in each one. So if you count 1, 2, 3, 4. So 1, 2, 3, 4, 1, 2, 3, 4. So knowing our previous, so if you take a look at the structure over here, you can tell that sort of that if you want an addition reaction to happen, you're going to need a double bond to happen. So the double bond was probably present somewhere around here. So that double bond was broken, and when it was broken, it started forming bonds with the other ones. So you have to look for a place where you could potentially put a double bond. So you could put it over here. It's kind of difficult to put it anywhere else because then this would, let's say if you wanted to put it over here, then this would automatically become part of that. So you need to take a look at the branches or the sort of functional units that are above as well, and then make a sort of logical deduction that, okay, where would the double bond be? So the double bond is going to be in these units over here, which ties in directly to our next question. Oh, so this one is going to be 3. So the displayed formula of the monomer, so if we take a look at it, you put a double bond over here. So you're going to get something like C double bond over here, and you've got one CH3 over here. So remember, because it's a displayed formula, you need to show all of the bonds. So this is going to be H. This is going to be the same thing here. H, 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 and this is going to be H. That's a nice, easy 2 marks there. And we're going on to the last bit of the question. Shows part of the general structure of an amino acid. Complete figure 6.2 to show all the atoms and all the bonds in the functional groups of the amino acid. So biologists, people that have biology, they know this one pretty well. And if you're studying for your IGCSE exam, you obviously have to know this. There's going to be a carboxyl group over here. So you're going to put a C over here, a double bond with the O, and you're going to put an O here. And then you're going to put the amine group over here. So NH2. So once you do that, that's a very easy mark to get. Oh, because it's a displayed formula, remember you have to show all the bonds. So my bad, I kind of messed up over here. H, there we go, much better. Draw a circle around one amide linkage. So the amide linkage is always going to be between this one over here. So you could draw one between here, you could draw one over here. It doesn't really matter which one you give. And the last question, very easy. State the name given to natural polyamides made from amino acids. If you are looking into sort of the nutrition community on social media, you know the word very well. It's protein. And yes, while protein is important, make sure you guys get your fiber as well. All right, next question, question 6. All right, let's take a look at this. Simple enough question. The first one, state the name given to group 7 elements. You should know it very well. This is halogens. All right, state which group 7 element is the most reactive. So if you take a look at the periodic table, as you go down the group, oh, that was a really bad arrow. As you're going down the group, the reactivity also decreases. As a result, the most reactive halogen is going to be fluorine. Give the physical state and color of iodine at room temperature and pressure. Again, a lot of people get confused with sort of the halogens. They think that they're all gases. No, fluorine and chlorine are gases. Bromine is a liquid that's volatile, and all of the rest are solid. So it's going to be solid, and the color is described as gray. Oh, maybe I should fix that. Yeah, gray, black. All right. When bromine is added to aqueous potassium iodide for a displacement reaction occurs. The reaction for the equation is shown. Write an ionic equation for the reaction. So this is interesting. Whenever you're doing an ionic equation, we want to take a look at which element sort of experiences the most ionic change. So if you take a look at potassium, potassium went from having +1 on this side to also having +1 on this side. I should write it over here, say +1. So immediately you get rid of potassium from your ionic equation. Bromine goes from having 0 to -1 because it goes from Br2, which obviously has 0, to 2Br, but it's bonded with potassium. So if potassium has +1, bromine is going to have -1. So you're going to include bromine there. It's going to be Br2 plus 2I. So what's the charge of iodine over here? If it's with potassium, it's going to be minus. And you're going to draw an arrow. Now bromine is the one with the negative charge, and iodine is the one that has a net 0 charge. So that's the answer over there. Iodine and bromine react at high temperatures to form iodine monobromide. The equation is shown. Structures of the molecule involved in the reaction are II, Br, and IBr. So we're given the bond energies over here, and we're asked to figure out the enthalpy change using the bond energies in table 6.1. And again, they're giving us steps. So let's take this one by one. Calculate the total amount of energy required to break the bonds in 1 mole of iodine and 1 mole of bromine. So 1 mole of iodine means you're breaking 1 I bond, which means you need 150 kilojoules. And you're also breaking 1 Br bond. So that totals to around 193 kilojoules. So if you add 150 with 193, you get 343 kilojoules. So this is the amount of energy you need to give to break both the iodine bond, covalent bond, and the bromine covalent bond. Now, whenever you form iodine bromide, remember, bond formation is exothermic, which means it's releasing energy. So because it's exothermic, you are getting, you have to check what bond is being formed. So you're getting an iodine and bromine bond. So IBr, this has a total bond energy of 175. But remember, you're not getting only 1 mole, you're getting 2 moles. So you're going to multiply this by 2. And that's going to give you 350 kilojoules. Now, whenever you're doing enthalpy change, remember the sign is very important. So total amount of energy released, so energy in minus energy out. So the total amount of energy you needed to give to break the bonds was 343. And the total amount of energy you received when the energy was given out when you broke the bond, when you formed new bonds, is 350. Now sign change is very important. This will be -7 kilojoule per mole. This will be -7. All right, we're right at the end. When sodium is added to water, a chemical reaction occurs. Give two observations when sodium is added to water. So if this was another group 1 element, let's say if this was, for example, rubidium, cesium, you could very happily write explodes. But thankfully, we're dealing with the less reactive sodium. So very simple, keep it simple. You're going to write fizzing, and you're going to write solid dissolves. Now, if you go on YouTube and you look up this video of sodium being added to water, you can also add that the solid moves, because sodium's, when you look at the videos, you'll see the sodium sort of skating around the surface of the water. So if you mention that, you're also going to get a mark. If you write that it's floating, you're going to get a mark. That's fine. If you write that, let's say it's melting, you're also going to get a mark. So there's a lot of things you can do, but these are sort of the ground rules. Thymolphthalene is added to the solution when the reaction has finished. State the final color of the thymolphthalene in the solution. Sodium hydroxide is alkaline. As a result, it's going to show blue. So we're going to end it with this. And that's that. So hopefully you guys were able to understand this paper. I don't think it was too difficult. If you found any question difficult at all, feel free to reach out. We're here to help you out in any way you want. And best of luck for the exam up ahead. I'm sure you guys are going to do great. You guys don't need to worry too much about everything. This has been Albab signing off. Thank you so much. This is a really fun thing to do, and I hope you guys stay with Fastpapers moving forward. Thank you.